Welcome to a new episode.
Hello and welcome back to the Convection podcast, where we explore the essential principles of construction science that every professional in the built environment needs to know. As always, I'm your host, Chris Bailey, and this is episode 10. Today, we're diving into a topic that's absolutely fundamental to modern construction: heat principles. Whether you're designing a new build, retrofitting an existing structure, or just trying to understand why your energy bills are so high, understanding how heat moves through the buildings is crucial. We'll explore heat transfer, thermal conductivity, condensation problems, and how sustainable design is shaping the future of our homes. So grab a coffee, settle in, and let's get connected to the science of heat in construction. So let's start with the basics. When we talk about heat in the building, we're really talking about three fundamental processes: conduction, convection, and radiation. Understanding these three mechanisms is key to managing a building's environmental footprint. So conduction is probably the most straightforward. Think of it as heat moving through a material or from one material to another via direct contact. At the atom level, heat is transported as atoms vibrate with kinetic energy. Now here's the interesting part. Some of the materials are brilliant at conducting heat, like metals, while non-metals and gases are poor conductors. This is why we use certain materials for installation and others for heating elements. Then we have convection. This is all about movement. Heat energy transfers from hot places to cooler places when particles with lots of heat energy in a liquid or gas move and take the place of particles with less heat energy. Picture a radiator in your room. The warm air rises and cooling at the ceiling and falling back down, creating a circulation pattern. That's convection in action. And finally, radiation. This is one difference because unlike convection and conduction, radiation doesn't need particles in a solid, liquid or gas. It's a type of electromagnetic radiation involving waves. The sun is 150 kilometers away, but we still feel its warmth through radiation. Pretty amazing when you think about it. So how does all this apply to buildings? Well, heat is lost from homes through all three mechanisms. We release heat through conduction in the walls, floors and roofs, and even windows. We lose it through convection when cold air enters through doors and window gaps, creating currents that transfer heat energy up to the loft. And we lose it through radiation passing through walls, roofs, and even windows. The good news is we have solutions. So carpets and curtains reduce heat loss. Double glazing, triple glazing is a game changer. Cavity wall installation prevents air from circulating in the gaps between your inner and outer walls. And roof insulation. That's one of the most cost-effective improvements you can make to reduce heat loss. Now let's talk about air itself, because air has important characteristics we need to consider. In the UK, we design heating systems from a temperature range from -1 to 21 degrees Celsius. That's quite a spread. Air also has density. And here's something you might not even thought about. The higher you go up in the atmosphere, the less dense air becomes. This matters for tall buildings and ventilation design. And then there's humidity. Air contains water vapor, which measures as a percentage. This brings us to one of the biggest problems in poorly designed buildings, and that's condensation. Condensation occurs when hot, humid air touches cold surfaces. Well, we've all seen this. Think of steam from a kettle landing on a cold window and producing droplets of moisture. But condensation isn't just annoying, it can be seriously damaging. It can occur on surfaces, that means inside materials like bricks or blocks in a cavity wall. Condensation particularly happens in buildings that are poorly heated, poorly ventilated and poorly insulated. The damp produced encourages mold growth, which can cause real health problems for occupants. So how do we reduce condensation? Modern building design tackles this through several methods. We use increased levels of cavity wall insulation, typically around 150mm wide now. We reduce air leakage from buildings. We're incorporating background ventilation, which allows air to flow into a building without the need to open windows. And we're using ventilation at source, extractors over cookers, fans in bathrooms to remove moisture when it's created. The effects of moisture on construction materials are significant and costly, so let's run through them quickly. Timber, when it becomes damp due to condensation over time, it starts to break down and rot, losing its structural integrity. Plaster becomes mouldy and disintegrates. Steel develops rust and corrosion. Paintwork gets covered in fungal spores that need treating and wiping off, often requiring recoating. And moisture can cause corrosion within electrical components and wiring, which then need replacing. These aren't any minor issues, they are expensive, time-consuming problems that proper design can prevent. Let's get a bit technical and talk about thermal conductivity. You've probably heard the terms like U values, R values and K values thrown around. So let's break these down. The U value is the total thermal resistance of a building, expressed as 1 divided by RT. This produces a value that must meet Part L of the building regulations. U values are always measured in watts per metre squared Kelvin. The lower the U value, the better the insulation. The R value measures the thermal resistance of a material. The higher the R value, the greater the insulation power. You calculate it by dividing the thickness of a material in metres by its K value. That is thermal conductivity. This information is crucial when selecting insulation materials. It's not just about the thickness, it's about how effectively that materials resist heat flow. Here's something else to consider: thermal expansion. All materials expand and contract due to temperature changes. If you don't allow for this in building designs, cracking does occur. For an example, every 6 metres in a block wall, there has to be vertical expansion joints to allow the wall to accommodate for temperature changes. Timber expands and contracts in relation to its moisture content, causing cracking. Green oak is particularly notorious for movement when it dries out. There are calculations for this. You need to know the original length, the coefficient of linear thermal expansion, the initial and final temperatures. These coefficients are always available in the manufacturer's data sheets. Let's shift gears and talk about something more forward-thinking: generating power for buildings. Photovoltaic cells create direct current through silicon conductors built into panels, so solar panels, and inverters turn it into AC at 230 volts, which we can use in our homes safely. We have heat recovery systems that take latent heat from exhaust air and recover it and use on fresh air. This is incredibly efficient and becoming more common in new build properties. Now, traditional gas and electric power are still very commonly used for hot water, radiators and underfloor heating. But gas boilers are slowly being phased out as the UK government tries to reduce emissions affecting global warming. Alternatively, more sustainable heating systems are being proposed, including the likes of ground and air source heat pumps. When it comes to heating and cooling buildings, there are both passive and active strategies. To cool a building, occupants can open windows to allow air movement and use shading to reduce thermal heat gain. To warm a building, they can close a window to reduce airflow and use traditional or heat recovery systems. From a design perspective, orienting buildings to face south maximises sunlight and warmth. These passive design strategies cost nothing to run and can significantly reduce energy consumption. For larger structures, there's combined heat and power or CPH systems. This is highly efficient process that captures and utilises heat. That's a byproduct of electricity generation. It's suitable for large structures or areas where there's a need for both electricity and thermal energy. So, for instance, manufacturing facilities, commercial buildings, that sort of thing. By generating heat and power simultaneously, CHP systems can reduce carbon emissions by up to a staggering 30%, compared to separate conventional generation via boilers or power stations. Finally, let's look at the future. Global temperatures are forecast to rise by 1 degree Celsius on average due to global warming. This could mean greater temperature extremes and impact demands for housing that can cope with different temperature ranges. Housing designs for the future need to consider climate impact on demand for heating and cooling, avoiding high energy demands from heating systems and air conditioning systems. In addition to innovative building design, even simple measures like painting roofs white could reduce heat buildup within cities. The buildings we design today need to be resilient, efficient, and sustainable for decades to come. Okay, so that brings us to the end of episode 10 of the Copper Connection podcast, where we have looked at heat principles in construction science. We've covered a lot of ground today, from the 3 mechanisms of heat transfer to condensation problems, thermal conductivity values, and sustainable heating solutions for the future. Understanding these principles isn't just academic, it's essential for creating buildings that are comfortable, efficient, and environmentally responsible. If you have found this episode useful, please share it with a colleague or fellow construction student or professional. And if you have a question or topic you would like us to cover in future episodes, please reach out to us. Until next time, stay connected to science of construction and keep building better.
We'll be back next week. In the meantime, please subscribe and thanks for listening.